is 0.98 and 1.02. So deadband is plus minus 2%. This one most probably goes 0.9 or even lower. So that tells you that how you want to define this slope, that how aggressive or benign you want to make this slope. And it will continue that. And slope can go, you can define it, say 0.8, just to reduce this slope. But another thing you have to remember, in the standard, from 88% to 110% is defined as the normal operating condition. Below 88%, above 110% are defined as abnormal voltage condition. And there are totally different requirements that how the DR should behave during the abnormal voltage condition. These are the functions. Okay, I'm hearing echo. So these are the functions defined for normal operating condition. So voltage might be 0.8. That doesn't mean that it will continue to operate till 0.8. It will be just dictate that at the edge of 0.88, what is the maximum reactive power will be available. So long answer to short answer to your question, it depends on the standard. If I'm not mistaken, the California Rule 21, the deadband is plus minus 3%, maybe 3.3% is the deadband, and this might end at 0.92 or 94. So California Rule 21, Hawaii 14H, IEEE 1547, they all have similar shape, but it changed from the deadband width, like IEEE has plus minus 2%, California has plus minus 3%. And this number may also change a couple of percentages. Okay, so few more examples. Maybe I can show a couple of examples. This is actually a test result of an inverter that we tested in the lab. What you are seeing is that this dotted line is the volver configuration that we configured the inverter. These blue dots, circles are reactive power absorbed or injected by the inverter, and these green crosses are this active power generation or watt. So what we did in every case, we started from 240 volt and then went to say 242 volt and then bring it back, 250 volt, bring it back, 260 volt, bring it back. So we kind of make a step change to go high voltage, see what the inverter does, and then bring it back. Similarly, other direction, go to low voltage and then bring it back, and then calculated the real and reactive power from the inverter. So what you are seeing, as long as the voltages are within the deadband, there is almost no reactive power, like these blue dots over the zero line, and the inverter was generating 6 kilowatt, its nameplate power was generating that. Once the voltage starts going outside the deadband, you can clearly see the reactive powers are increasing. These are each a test point. So each higher voltage is generating more and more absorbing power. And you can see the corresponding power value if you go vertically, power value. So immediately after a couple of voltage points, the real power did not change because maybe this inverter has some reactive VA limit available that it can do reactive power of certain magnitude without reducing real power, if you remember that Pmax and Smax question. But at certain point, when reactive power becomes large, it has to reduce the real power to produce the reactive power. It's a 6 kilowatt nameplate. So at this watt, it has to reduce the power to provide the room for reactive power. And you can see that above this limit, when it becomes saturated, voltage goes high further to 60, but watt did not change. It remained the same after once it hits the saturation limit. And at that time, once the VAR is fixed, real power also not changing in the high voltage side. Opposite behavior in the low voltage side is injecting VAR automatically. We did not make any changes in the setting, just change the voltage magnitude. And it start injecting VAR, and again, same thing, saturated. Above the VAR injection, it was reducing the real power to make room for that. One difference you see on the high side, once the reactive power becomes saturated, real power is also saturated, did not change. But that's not the case in the low voltage side. Once VAR become fixed, not changing, with the further lowering the voltage, because we are now doing 230 volt, 220 volt, 215 volts, so we are lowering the voltage further. And you can see that real power is keep on decreasing. Anybody can explain why is that? The low voltage side, it failed to maintain the power once the reactive power became fixed. The power was not, active power was not fixed, it was keep on reducing. which did not happen on the high voltage side. Anybody wants to guess or explain why is that?
I'm going to guess you're current limited.
Exactly, absolutely right. So what happened on the high voltage side, voltage goes high. To maintain the power, it needs less current, which is perfectly okay because it's below its threshold. In the low voltage side, it can try to increase the current, but at a certain point, it will hit its current limit. And once it is current limit, it has no room to increase current any further. So after that, if we keep on reducing the voltage, power will keep on going down. Because voltage is low, current is fixed, power is going down. So that's exactly is happening in the low voltage side. Thanks for the answer. So this type of behavior you'll need to also to explain the inverter operation at different voltage range. Okay, so next topic showing some dynamic behavior. Because what we are showing here is the magnitude of reactive power in response to the voltage. But this figure doesn't show how long it takes to get from 0 watt to X var. What is the speed the inverter changes the reactive power? So that's the next part. We're showing this type of dynamic test. So what you are seeing here is that we change the voltage, which is the this pink or magenta color. So from 0 volt, it going high voltage, step change, very sharp change, staying flat, and then going to the opposite direction with a step change. Then 0 volt again, nominal voltage again, then a slow ramp, and then a fast ramp. So basically, we are checking different speeds the voltage is changing, and in response to that, how the inverter is changing its reactive power. And you'll see this number here. The vendor call it adjustment time. You can call it response time or open loop response time. So it can be called different names. So for example, this example is for 10 seconds. You can clearly see voltage change. Inverter is changing relatively fast, but you can clearly see a slope, which is this kind of a representation of the 10-second timing that is taking time to go to the final value. Same thing, it changed abruptly, but the reactive power from 3000 negative going to 3000 positive takes some time, relatively slow speed. And same thing is happening with the change of voltage. Slow, it's changing slowly. Voltage change fast, it's changing fast, but not fast enough to reach to the limit before voltage start changing the other direction. So just see this figure, and then immediately next slide I'll show where this number will be adjusted to 2 seconds. So make it faster speed to change of reactive power. And inverters offer those type of adjustable parameters. And you can clearly see if you compare these two, it's a 2 second is almost a step change. You don't see that slope anymore. Almost abrupt change, and this is also change here. Similarly, you can see this speed. It managed to follow the fast transition and managed to go all the way to target bar, stay flat, and then come back that direction. So I'm showing this just to show that not only the magnitude, the slope of Q and V can be configurable. Similarly, the time can be also configurable, that how fast or slow the inverter respond to the change of voltage. And being a power electronics, of course, it can change within even a subcycle. It can change from injection to the absorption. But from power system point of view, you may not want the device to respond that fast, unless you're relying on that for voltage regulation or stability, a lot of other things. So that's why the standards and the manufacturers offer a range, depending on where you're located, how you're operating the system. Again, another responsibility utility might be to identify those speed also, that how fast or slow you want the inverter to respond to your voltage change. Do you want your cap band regulator to react fast before the inverter does? Or do you want to use the inverter as a fast device that reacts and then reacts the capacitor and your regulator? So those are the coordination question as a utility. How do you want to operate the system? What is the typical industry adjustment time for transmission level PV inverters? Honestly, I don't know the answer, and I also don't know if there's any typical number. These are, especially transmission level is more difficult because you have so many other things regulating the voltage. Do you really want the plant to do the control, or you want plant to be the slow response through a plant controller as a kind of your auxiliary or backup, where you have other resources to regulate the voltage? But honest answer is I don't know the number, and I also don't know if there exists any typical number. And you also have to remember that these are relatively new, like especially for US. Germany, maybe they're using it for a couple of years now. In the US, relying on the plant to do VOLVAR, do reactive power support to voltage regulation is still relatively new, I would say. Transmission, most probably write-through and frequency functions are used for some time. I'm not sure even transmission level operators are relying on plant for voltage regulation yet, but I might be wrong. I don't have much experience with the transmission level system. Anybody on the line who are transmission side of the business want to answer that question? Or know the answer? What is the typical industry adjustment time for transmission level PV inverters? Or even at the transmission level, are you guys activating VOLVAR function? I'm pretty sure there are some transmission experts on the attendee list. Okay. Okay, feel free to put your answer in the chat question if you don't want to speak up. And in the afternoon, I'll discuss that IEEE has a range. I think default is 5 seconds and adjustable between half a second up to 90 seconds. So you can see how wide that range is, because we think that depending on the location, depending on your operation or your philosophy of voltage control, different utility may want to use it different ways. So standard allows a wide range. I think half a second is the fastest, and slowest it can go even up to 90 seconds, and default most probably 5 seconds is response time. So anyway, so most of the time we show VOLVAR, which is Q and V relation, and we don't show the time, but time is another important factor. And also we have a separate research, and we published, we did a couple of webinars and also going to publish a report that if you select too aggressive VOLVAR setting, like very aggressive VOLVAR setting, and what is the response time, the combination of that can also create an oscillation problem. So I need to be careful about that, so that depending on the response time, what is the maximum slope you should be using to avoid any risk of oscillation, voltage oscillation. So those are more details, and we are going to publish a report this year, and we already did a couple of webinars on that topic. Okay, so a few examples again from the field. This is a megawatt scale plant, and what you are seeing is the 2 different days. One day VOLVAR function was on, and the other day VOLVAR function was off. Of course, I'm showing an example where it was very obvious that VOLVAR function maintained to reduce the voltage variability, almost flat, and lowered the voltage also compared to the VOLVAR function off. So this is an example where you are seeing the expected behavior that VOLVAR should effectively reduce variability and also reduce the voltage. But we have numerous examples where something else on the feeder is more dominating than the reactive power from the plant, and we didn't see any clear conclusion. But this is an example of that. If it's worked perfectly, then what you can expect to see. This is an example from a residential setup. A lot of residential houses with smart inverters. You are saying 3 consecutive days. This is the VOLVAR configuration. You can see the deadband was 0.98 to 1.02, and then the slope goes even beyond that. So the point that I'm highlighting here is that the bottom figure, the y-axis is the voltage, and you can clearly see that whenever the voltage exceed 1.02, for example here, only those incidents the plant the inverter was absorbing VAR. This is nighttime, so that's why nighttime is not doing anything. Again, this is exceeding the voltage, reactive power is going up. As voltage goes high, reactive power goes high, and then follows that. So 2 points I wanted to highlight here, that VOLVAR absorbs or injects VAR only when voltage goes outside the deadband. And this is an example of for 3 consecutive days. The other thing you're seeing that here voltage did not exceed, but still there are some reactive power absorption. What is that actually for then? Any answer? So one potential answer could be that because of this VAR absorption, the voltage did not exceed the limit. If this VAR was not there, most probably resultant would be a slight increase or above 1.02 voltage. So by absorbing this VAR, the inverter managed to keep that voltage below 1.02. So that's why you see some incidences that small amount of reactive power absorption managed to keep the voltage below 1.02. Some cases it absorbed the VAR but did not manage to bring the voltage all the way to 1.02. Maybe it reduced it compared to where it could have been, but not able to bring all the way down. So this is one thing that clearly says these VOLVAR power factor function are voltage regulation support function. Not necessarily they'll be able to bring the voltage within your target range. So it helps, it tries to regulate the voltage or tries to keep the voltage to the target level, but not necessarily they'll be able to do it because that depends on a lot of other factors. And here it is defined from the regulators that you guys typically use. If I'm not mistaken, I'm not the expert, but if I'm not mistaken, regulator keeps on changing the tap positions until it brings the voltage within the acceptable tolerance, like your target range, or it maximizes step size or final step. But it keeps on trying within certain time interval. But VOLVAR power factor are not like this. Based on the target, based on the characteristics, it will generate the VAR or absorb the VAR. Resultant of that, of course, it will have some improvement, reduction, or increase of the voltage, but not necessarily will bring all the way back to the target. So this is proportional control, but not proportional or integral control. So integral part is not there unless it's a closed loop voltage control. So that's another. So that's why ideally we should be calling it voltage regulation support function, not necessarily actual voltage regulator. Question, comment? Okay, let's see a few more examples. Again, this is another example from a kind of a commercial size facility, 100 kilowatt system. So two things we are showing it here. Left side we are showing is how accurately the inverter is following the VOLVAR curve. So a lot of our demonstration project, we look for a couple of things. One is that how accurately inverter is following the target curve. So we use the measurement data to overlay with the target and compare the performance. And of course, to see what is the impact on the voltage at different locations. So from this figure on the left side, you can clearly see the inverter is following the voltage at its terminal. Then it's pretty closely following the target, both in the low voltage side and high voltage side. And you can see that this particular location voltage actually went both high and low. And corresponding, the inverter absorbed VAR here and injected VAR here to help the voltage regulation. On the right side, what you are seeing is the three different locations. Again, same thing we are showing. This is a library building. The inverters were on the rooftop of a, I think, 4-story building. So inverters are on the rooftop, and we have a measurement system there at the terminal of the inverter. Then all this AC connection came down on the ground level, where their service panels are, like the electrical room. So most probably almost 200 feet or more than that, 200 or 300 feet from roof, the AC cable comes to the service panel, a switch gear, and then from there it goes to the distribution network within the campus. And we also have a monitoring system at the campus entry point. This is a university campus, peak load maybe 5 megawatt, and winter load or lowest load is 1.2, something like that. So we have monitoring point at the inverter terminal. We have monitoring point at the service connection point, which is almost 200 to 300 feet from the inverter, and then main campus entry point. So what you are seeing here is that blue is the baseline days where inverter was operating at unity power factor, and green several days where plant was operating at this VOLVAR function. And you can clearly see this case voltage is pushed on the right side. And if you notice the VOLVAR curve and its VREF point, you notice that this particular case VREF point was 1.02, not 1, which is typically not the normal case, but it maybe has some other use case. Variability or something was the use case. So VREF was 1.02, and that's why you're seeing that it's pushing the voltage high rather than lowering it down. And it was effectively doing it again, same thing. At the terminal of the inverter is very effective. It was able to push our median voltage on the right side and maybe relatively tighter band also there. It was also noticeable at the inverter or switchgear panel or the service entry point of the building. Still, it was pushed high and much tighter compared to the unity power factor days. However, if you go to this campus main point, which is like 5 megawatt load, and we are talking about only 100 kilowatt inverter, so of course there was no noticeable impact on the campus entry point. So that again shows the relative magnitude of the reactive power support from the DR has will dictate the actual impact on the circuit voltage. Some location it can definitely help. Other location it may not be strong enough to push the voltage further. So those are the couple of things just to show an example from real world. If you have any concern in your utility that whether Volvar is really works or not, we have tons of examples like that we have demonstrated that last 4 or 5 years in different locations that yeah, it works as long as it's a certified product, designed properly, configured properly, it should work. Here I'll show actually a actual video. It's a measurement data, all real field data. We just put it into in a video format to see what happens in a whole day from sunrise to sunset, power change, reactive power change. You'll see it here. You will see the voltage variation here throughout the day. A couple of times you'll see a step change. Those are the regulator or cap bank switching. And here, this is the configured Volvar curve. If you notice it, there is no dead band. We actually configured that in the field for a megawatt scale plant. And this particular case, the reference point was somewhere around, I think, 1.02. Sorry, yeah, 1.02, something like that was the, no, 1.1 maybe the operating reference point. So I'll play the video. You can, all these points will be moving. So basically showing the time lapse situation. So this early morning, plant just start to generating, and this is trying to find out the point so that it can follow the Volvar. So it does start from 0. Now it found the Volvar and trying to maintain it there, depending on the voltage variation. So here you're seeing voltage variation. Okay, my cursor is not moving. So lower left corner, these jumps are regulator or cap bank operation. And you can, whenever there is a jump, you will see there's a jump in the dot point also. That it suddenly voltage change, so it has to make a big change. So real power change here on the top. Reactive power is based on whatever the inverter is doing based on Volvar function. End of the day is shutting down, so power is going 0, is going back to its sleep mode. So let me know if anybody wants to see it again. So this is how you can expect the plant to behave throughout the day, sunrise to sunset. Power will go up, voltage will change throughout the whole day depending on the load, depending on the generation, depending on your other regulating devices. And it will try to follow this curve based on the voltage that it sees and try to absorb or inject proportionate or following this curve the amount of reactive power it's supposed to do. Anybody wants to see it again? Yes, no? Okay, looks like no. Let's move on. Actually, I have one more video, so you can see a similar thing, but a little bit different. Here you'll see, I think, comparison of a unity power factor day operation. So first half of the time you'll see a day when it was unity power factor. So you most likely will not see any reactive power, and voltage will be more distributed, widely spread. Then second half, you'll see a second day when this Volvar function was activated. And you can clearly see this Volvar is, again, no dead band. The reference point is literally higher, 1.03 is the VREF point, much higher. So should see the voltage was pushed higher direction and very aggressive slope. So if you say if 1.03 is the VREF, within 1.04, it went to its maximum bar. So compared to other situations, pretty aggressive Volvar setting, slope setting. So let's see. So first you are seeing the day when the unity power factor, so almost no reactive power, voltage going up and down. These are the histogram of the voltage for the whole day. and you can see pretty widely spread and almost no reactive power. Now the second day when it is this volt-var function is active, so you can see based on the voltage, reactive power is going up and down, and the corresponding voltage. So if you compare the 2 days of the voltage pattern, you can clearly see when the volt-var function was active, more and voltage was centered around 1.03, which was the reference point. So it injected and absorbed var to bring the voltage both directions. If it was lower than 1.03, close to 03, it was higher than 03, then being close to 03. So that's why you're seeing more concentrated around 1.03 compared to the other day. And the amount of reactive power, of course, depends on the amount of var it has to absorb or inject continuously. So that's kind of another example and comparison of 2 days. So it looks like only early morning there was a situation when it has to actually inject var, but rest of the day it was absorbing var. So that means voltage was high, even higher than 1.03. So by absorbing the var, it managed to pull all these voltages down to below 1.04. It has managed to do that. If you notice it, I can bring my laser back. So now unity power factor day, most of the voltage are large amount of time, voltage was higher than 1.04. So by absorbing this much of var, following this volt-var curve, like it was mostly operating in this part, it managed to bring most of the voltage below 1.04. So that's the comparison here. And you can see from this plot also, unity power factor, the voltage was higher, sometimes was crossing even 1.05. But this day it did not cross at all 1.05, and most cases it was below 1.035, maybe below 1.04. And these are all field data, so these are not simulations. Any question? We are running out of time, but let's see how far we can go. Again, this is the same example that I have shown before, a little bit reconfigured our test setup. Rather than making all of them home run, then we create a junction box to make it more one system impacting the other system, and then created this setup. And the main thing I wanted to show is the comparisons. So what you are seeing is basically 3 houses and the transformer secondary, 3 different test conditions. One condition was everybody was running unity power factor. Then second condition, everybody was running at 0.95. Everybody means 3 inverters running at 0.95. And then 3 inverters running at volt-var curve 1, which is defined here, plus minus 2%, and then 92 and 108. I believe this is the IEEE default setting, but we can check in the afternoon. So what you are seeing is the voltage observed at the 3 houses, their service panel, what voltage they have seen in the 3 different test conditions, and also what the transformer secondary have seen at this point. So you can clearly say if it's a unity power factor, voltage was highest. And this particular case, based on this setup that we created, the voltage went almost 10 volt higher when 3 inverters were generating around 5 kilowatt each. So total 15 kilowatt backfeed through this transformer. Each house almost saw a 10 volt increase in their service panel or point, a metering point. Then when you activate the 0.95 power factor, almost all the cases voltage was below 244. So significantly reduced the over voltage almost by 6 volt for all 3 houses, and similar impact you can see transformer secondary also not seeing same level of high voltage when it's operated at 0.95 power factor. When it was volt-var 1, which has 2% dead band, so it was not doing anything until voltage exceeded 1.02. So remember that part, that it only started absorbing var when it crossed 1.02, and since it may not reach all the way to 1.18, it did not absorb the maximum var it can absorb. Maybe it was operating mostly in this part, maybe up to 1.04, 1.05, I don't know percentage-wise what will happen. So it did not absorb the maximum it can var because the slope was not aggressive, but still it managed to reduce the voltage depending on the var it absorbed. You can see that at least a couple of volts, maybe 2-3 volt reduction was done by the volt-var function. So just to show the comparison that yes, both power factor and volt-var can help to reduce voltage, But of course, the magnitude will depend on how aggressive the setting is. So same test, before you saw the voltage in 3 houses, voltage and the transformer voltage. Same test, we are just showing active power. So 3 houses, 3 different test conditions, what was the power generated by the 3 plants. If you notice that all 3 houses reached to their maximum 6 kilowatt almost early morning, and then stayed flat for a longer period and then came back. So remember, this will be important. We'll discuss that in the next couple of slides. This is an impact of high DC to AC ratio. So if you know what I'm talking about, that most plant designers now put a lot of solar panels behind a smaller size inverter. And we'll discuss that why they do it. But result of that is that for longer duration, power will be flat, and the longer duration voltage will be also high and flat. So voltage will be flat at high value for longer period in a sunny day. So that will be the outcome or resultant of the installer putting a larger size panel behind a smaller size inverter. So power is same, even if it's a say 6 kilowatt inverter, they may have put 7 kilowatt DC. Inverter will never exceed 6 kilowatt, but what will happen if you reach 6 kilowatt early and then remain there for longer time, that's what's happening. So one question that I have, looks like house A and house C, for unity power factor operation, power was reduced. You can clearly say compared to unity and Volvar, 0.95, active power was reduced for house A and house C. But for house B, even for 0.95 power factor, there is not much reduction in the active power. What is the reason for that? Again, who can answer that question? Please unmute yourself, answer, or put it in the chat option. I'd like to hear answers, even if in educated case. We already discussed the reason. Any guess? If you guys are paying attention, I see a lot of symbol shows that you guys are not actively monitoring your screen or maybe not doing anything. This is one limitation of doing online. If it was in person, I definitely would have been get some answer by this time. Okay, I think it's an answer. You have to give up real power to get the reactive power with 0.95 power factor. If that's the case, then it should be happening for all 3 houses, all 3 inverters. Why is happening only inverter in house B but not in house A and house C? Remember that there are different inverters in different houses, not the same brand. Inverter is current limited. That's not the case here. So if you remember this discussion that we had before, house A and house B have same secondary, not really. House A and house B, the length is different. I think one is 50 feet, another one is 150 feet to the junction box. So a little bit different is there. But you're right, voltage is also different. If you remember the discussion that we had, P max and S max, so looks like house A and house C inverter is 6 kilowatt and 6 kVA. So whenever we ask for reactive power, it cannot maintain the 6 kilowatt anymore. On the other hand, house B inverter was 6 kilowatt, but most likely 6.6 kVA or maybe 6.5 kVA. So it has a little bit of VA available to provide reactive power without reducing power from 6 kilowatts. So that's what is happening here. It will happen only up to certain power factors, 0.95. We did this same test for 0.9, and you'll find that in the report that I showed earlier. That case, even house B was reducing power because now it's too much reactive power and it cannot do that without reducing real power. So that's what is happening here, that house B inverter is larger VA rating than its kilowatt rating. So even if you are in a position that you have to answer this question that, oh, because of power factor will work, now I have to reduce my real power. One simple solution could be use an inverter which is a little bit larger size, at least the VA rating is a little bit larger. So that will have a lot of room for reactive power support. Any question or comments? Somebody unmuted? Okay, if not, let's move on. The last result I want to show from the same test is the amount of reactive power absorbed by each of the three inverters. And you can clearly see unity power factor, almost no reactive power. This particular case, 0.95 was a lot of reactive power absorption because of it's a proportionate to real power. Power goes to 6 kilowatt, it's to 6 kilowatt for 6 hours. So reactive power goes to 2 kilowatt kVAR and remains there for 6 hours. On the other hand, volt-var start absorbing var only when voltage exceeded 1.02. That's what you are seeing here. And also when the voltage came back below 1.02, there is no reactive power. So it's doing reactive power only when the voltage was above that. And it did not go to its, anywhere close to its maximum that it can do 3 kVAR. It was only doing 500 bar. So that's why it was not impacting the voltage that much. If I would have made this slope sharper, like 1.02 and then it ends at 1.04, then we would have seen it's a lot of var absorbed by the inverter, even in the volt-var mode. Okay, same example, just showing it for a highly variable day because these are all clear days, perfect sunny day. But what happened in a highly variable day, and you can clearly see this is what the voltage they look like. Go up and down, up and down, up and down all day. This is real data. So the irradiance came from a site where we had the measurement. We put this irradiance into a PV simulator and then expose the inverter to these three different, the cloudy condition with the actual irradiance measurement from the site. So this might be somewhere in Florida, this type of variability. So whole day irradiance is going up and down, power is going up and down, correspondingly voltage is going up and down. For unity power factor, and then both volt-var and power factor managed to reduce the variability, the fluctuation, and also the average was low that we have seen before. But not only that, it was also reduced the variability relatively compared to unity power factor. So that's what is the advantage of having some sort of grid support functions active. Any question? Okay. Next, it's not directly related to the smart inverter, but this question may come into your day-to-day operation that any aggressive volt-var or power factor setting, how may impact customers' revenue. So that's why it might be good to know the background. So first thing I wanted to highlight is that what do we mean by DC to AC ratio? If you are not familiar with this term, basically it says the amount of PV panels, so aggregate DC capacity of the PV array. So you put, I don't know, 300 watt and then 100 panels in the system. So what is the total DC rating of the plant? That's the PDC rating, PDC. And you may have 5 inverters, each to 220 kilowatts. So total AC rating will be 100 kilowatts. So this ratio is known as DC to AC ratio. Sometimes it's called overloading ratio. There are a few other names there. But the basic idea is that total DC rating of the plant divided by total AC rating of the plant, so DC to AC ratio. In the past, when panel price was pretty expensive, 5 watts, $5, $6 per watt, nobody thought about putting extra panels there. But now, you all know that PV panels has dropped significantly and pretty cheap now, PV panels. So installers, depending on the location, depending on the site, a lot of factor goes into that. They have the tendency of putting larger size array behind a smaller size inverter. And even maybe 5-6 years before, the ratio was 1.1, 1.2 was the normal ratio because of the DC losses and other things. But now I have heard 1.4 to 1.6 is pretty common, 1.4, 1.5, pretty common. Some cases I even heard 1.8, even 2x the DC size. So for example, you can think about 1 megawatt AC will have 1.5, 1.6, 1.8, even 2 megawatt DC installed behind it. So that's what is happening, and most probably as a utility, you have no control over that because this is a customer choice. You can put a limit on how is the maximum AC power they can inject to your system because of the hosting capacity limit and other reasons. But DC, most probably you don't have any control. So why they are doing it? Because panels has, even if it's cheap, it has some cost. So I'm trying to explain that from this figure that if you have a say 1.15 DC to AC ratio, you can expect to see a behavior like this orange curve. That sun goes up, power goes up, middle of the day, full sunny day, middle of the day, it may reach to the maximum power for half an hour, 1 hour type of scenario, and then comes back. That was the behavior, or it will be still the behavior if the DC to AC ratio is low. Now, if they use 1.4, 1.5, 1.6, what will happen? Even at 10 o'clock, there will be enough sun, say 800 watt per meter square, to generate enough DC to push the AC power to the limit. So that's what is happening, that even with lower irradiance, because of excess DC energy, the power generated by the plant is going up faster. And maybe by 10 o'clock, it will reach to the maximum. Once it hit the limit of the inverter that it can take, so inverter is a 100 kilowatt inverter, it can take maybe 110 kilowatt DC, and then 10 kilowatt is lost inside the inverter. So once the DC hits 110, inverter will not take any more DC power. And after its conversion, it will go into 100 kilowatt, and that's what you'll be seeing rest of the day, or as long as the irradiance remains high, and then the power will come back when the irradiance goes down. So this is what happened when you say the high DC to AC ratio on a clear sunny day. It's not that plant is generating more power. Power will never exceed the AC rating of the inverter, or should not. What will happen is that it will generate more energy, and that's what you are seeing. This shoulder part is generating more energy. So this is the reason why the installers put extra DC. And of course, there will be a break-even point, that at what size this extra kilowatt hour generates enough revenue that pays for the cost of the panels. And that may depend on the geographic location, number of cloudy days versus clear days. A lot of factors goes into that. But this is the main concept, that why they put extra panels. And of course, there are degradation. Maybe if you're familiar with that, year by year panels get degraded by 0.5% or 1/4%. So even if it's 100 kilowatt today, 5 years later, it will not be 100 kilowatt anymore. Temperature is another factor. A lot of cases, DC generation, it depends on the temperature. Like if you're Arizona, your high temperature will reduce the power production from the panel. So a lot of factor goes into those decisions. Is there a reason to do this to offset dirty solar collectors? That could be another option. If in a location like a desert type of environment, you have a lot of dust, maybe they will, rather than doing a periodic cleaning, they will do, okay, throw some extra panels to generate more DC. So those could be all, as I mentioned, that the decision is, the reason is simple, but how they calculate whether it should be 1.5, 1.6, 1.8, what is the break even, that depends on a lot of factors. Okay, so what happens on a cloudy day? Of course, cloudy day, you may not have enough DC to even reach to the AC power, but you can clearly see that because of higher DC to AC ratio, the plant will generate more kilowatt hour. And that's kind of the explained that the justification of having oversizing, especially if you're an environment where you have a lot of cloudy conditions. There's a comment for PV plus battery plants. Is it common to use clipped energy to charge batteries? Very good point. Yes, that's the potential that possible. This clipped energy, which is otherwise wasted, basically it will just make your panels temperature will go up. But if the PV plus battery project is designed correctly, again, there are a few factors there. In the hybrid system, the charge controller or the DC-DC converter that is connected with the PV panel has to be large enough. Inverter could be small. Say, for example, inverter is 100 kilowatt, PV panel is 150 kilowatt. If you put that PV panel directly to the inverter, you still have the clip energy. But if there's any DC-DC converter of size of 150 kilowatt, then it will convert the entire DC power from the panel and generate maybe 146 kilowatt, 147 kilowatt. From there, inverter will take only 105 kilowatt, and remaining 40 kilowatt will go to the battery and charge the battery. So that's possible if I showed the different topologies, I think, on Tuesday. The DC-DC converter used in front of the PV panels, if that's large enough, then you can entirely transfer the DC generation from the PV into two directions. One goes to inverter, another part goes to the battery. Yeah, that's possible to capture the clipped energy. And some of these vendors will identify that as one of the benefit of having hybrid system and having a larger DC-DC converter. I hope I answered your question, but let me know. So I already mentioned that what is the impact of that? Of course, you have more kilowatt hour generation. So this is what you are seeing. 1.1 is the blue one versus different ratios, 1.3, 1.4, 1.2 for three different houses. And each cases, you can see that oversizing generates more kilowatt hours for those three houses. And of course, the result of that, in the blue case, your high voltage was for maybe an hour, but for the higher DC ratio, your high voltage is for 4 hours, 5 hours. As a utility, you will see the side effect of that. This high voltage is there. It's not only there for high voltage, but it's now for longer periods, the high voltage. So whatever mechanism or correction you apply, that has to operate for now longer duration compared to 1 hour, which was the case before. So as a utility, you guys have to now handle this high voltage for longer period. I think I discussed that before, so maybe quickly pass that. The same the comparison of kVA versus kilowatt. If it's 100 kVA, 100 kilowatt, the moment you ask for power factor, it has to reduce to get you this 44 kVAr. If it is slightly oversized, like 100 kilowatt but 111 kVA, it can do the same 0.9 power factor without reducing the power. So that's the example I'm showing you on a numerical example. Now, what is the impact on the higher DC-AC ratio? So before this red curve, if you remember the previous slide I showed, low DC-AC ratio, red curve where the orange color is the power generation. With the higher DC ratio, this black one is the power generation. And no point AC output will be exceeding the rating of the inverter, so that's fine. Now, either for power factor function or Volver function, if the plant has to generate some reactive power, so for example, I'm now giving example of this scenario, that this is the same rating. Now you ask it to generate 44 kVAr because you want it to operate 0.9. So that means now it has to reduce the power to generate this much of var. So there's the example. Think about this is that example, that it has to reduce the power to provide the reactive power. Now if you compare the loss for the customer with lower DC ratio, this was the amount of energy loss due to the reactive power support, the white area between the orange curve and the red curve. But if the DC ratio is the higher, 1.4, the loss will be this trapezoidal shape area. So between the black line and the red line, this will be the amount of energy lost on a clear sunny day. So you can clearly say for a higher DC-AC ratio, reactive power support, especially for system where kilowatt and kVA rating are same, the plant will have more losses or energy loss due to the reactive power support. But again, if the kilowatt and kVA rating are same, if there is some kVA available, then this question will not arise. So same thing here, in a low DC ratio, almost no loss due to the reactive power, but for high DC, even for cloudy day, it may incur some losses there. So I'm just showing this, these are relative terms, these are not actual numbers, but possible. Any questions? So that's why again goes back, you may need to select a power factor Volver that is enough to solve the voltage, not go too aggressive. The same thing I'm showing with the example that I showed before. The voltage goes up and down, and this time I'm showing the active power also, that what was the active power generated by the plant. So this is a 6 kilowatt inverter. When there is no VAR, you can see it is generating 6 kilowatt. The moment we ask for 3 kVAr, absorption or injection, you can see the power has to be reduced to do that, to generate that much of power. So from 6 kilowatt, most probably dropped to 4.8. So almost 1.2 kilowatt real power was reduced whenever there was excessive reactive power demand. When the reactive power goes 0, power goes back. So these are all autonomous. So inverter will do that, especially if it's in the Q priority mode. So the moment you ask for Q, it will reduce the real power to give the Q. When there is no Q demand, it will go back to the normal operation as long as sun is present or DC energy is present to generate 6 kilowatts. So that's the example here. Any question? Again, this is a test result. Any question, comment? Okay, so we managed to finish power factor and volt watt. Let's try to wrap up the volt watt before the break. Then rest of the things we have to do it in the afternoon session. Hopefully we'll have time. So far the two functions, those are both reactive power based support function. Now this is the only one where you're actually touching the active power. And remember that since it's active power, it's more sensitive than reactive power, because now any reduction on active power will have direct impact on the revenue for the customer or whoever is owning the DER's plant. So that's why it's very sensitive, and use of that is also need to be some thinking before it. But first, let's discuss the actual behavior. What does this function actually mean? So what you have is the active power generation on the y-axis, and the x is the voltage at the inverter terminal or wherever you want to implement this function. Say plant level at the PCC. So then PCC voltage will be the x-axis. So what it says that up to certain high voltage. So this is 1 PU up to certain high voltage, which is configurable, is a user configurable number. You let the inverter to generate or the plant to generate at its rated power. So think about this is the rated power. So up to certain threshold, plant can operate normally, generate up to its maximum rated power it can generate. If the voltage goes above that, then its maximum generation, it's not curtailment, its maximum generation will be limited by this line. So this magnitude will say at that voltage, what is the maximum the plant can generate. If it generates less than that, no problem. But if it has the potential to generate, say at this voltage, it has potential to generate this much, then it has to reduce it to this level. So that's what the volt watt function means. This is not a direct curtailment. This is basically say at that voltage, you can generate maximum that much, or even it's not generate, you can export to the grid maximum to that. One option could be you do curtailment, or other option would be you still generate and then charge your battery or use it in your load as long as you don't inject to the grid. So that's kind of the main idea of this function. And at certain voltage, it will reach to its lowest steady state operating point. Say, for example, this inverter cannot stay connected when the power goes below 10%, or for safety reason, it wants to shut down. Whatever the threshold, and what voltage it can, then at that voltage, it will go to that power level and stay flat there. So after that, even if the voltage goes high, it will not do anything. And of course, at certain point, it will hit the trip voltage. For example, as per IEEE 110%, the DR is supposed to shut down at within 2 seconds, I think, or 1 second. So that's the trip magnitude. So if I want to show the simulation, say voltage gone up, but it's still within the V prime. So there is no change in the real power here. You can see there. Now after that, if the voltage change goes further high, even if it has the potential to generate this much power, it has to reduce it to this level. So that's what is showing it here. If you go back, it was generating this much of power, and assume that there is no change in the DC. If the voltage goes up, it has to reduce the power from there and go here. So that's what it means, that you have to reduce it here. If the voltage goes back, power can go back if this DC power is still available. So that's what this function means. If I want to show a test result, again, this is a test result in the laboratory, not in real field. So that's why we configure it for 102%. So very aggressive, that if the voltage exceeds 102%, you start reducing your power. At 107%, you go to the 10% power level and then stay flat. So that's how this configuration curve means, that up to 102% normal operation, above 2% start reducing your maximum generation or injection, and 107% reach 10% and then stay connected. And that's what you're seeing here, that we configured this, then we change the voltage, which is the red color, from 275, so three-phase system. 1 PU, from 277 it went to almost 297, which is corresponding to 108%, and stay flat and then came back down. So the result of that, you can clearly see that once the voltage exceeds 1 or 2%, so not immediately, but once 1 or 2%, it starts reducing the power, reach to the 10%, which is only 10 kilowatt of 100 kilowatt inverter, reached to a 10 kilowatt, which is 10%. And once the voltage came back, the power went back. So this behavior or this operation is autonomous. Once you configure the volt-watt function, it will follow that curve and increase or decrease the power based on the configuration. Now, two things I want to highlight here. I mentioned that this is a laboratory testing, and that's why we set the 1 or 2%, which is very aggressive for volt-watt setting. The idea is that the normally, as a utility, most of your voltage varies 2-3% pretty regularly. It can go to 1.3%. Secondary voltage maybe go a little bit higher. You don't want to use volt-watt function as your day-to-day regular voltage regulation mechanism. You are expected to use the volt-var function for that, or even power factor function for that. Try to solve the voltage using reactive power, which may or may not impact the active power generation. What you should be using volt-watt function for, that you tried your reactive power, but still voltage is going high, say 105, 106, 107. So you should configure the 1 or 2% to somewhere like 105, 106, that, okay, now voltage is, even if I tried, but still voltage is going high, at that point I'm trying to reduce the power. That will, of course, impact the revenue, but what is the alternate? If I don't do anything, voltage may go to 110% and shut down. So what you are offering the customer, rather than abruptly shutting down, trying to reduce the power, to keep the voltage low so that you don't have to go to the shutdown phase. Because once the inverter shut down, it has to go through the 5-minute waiting period and then come back and may still see high voltage. So this is kind of the alternative to the shutdown, as long as you are not setting the power reduction at something very close to nominal voltage. So for test purpose, we did it, but I think in real recommendation is that you use kind of a belt and suspender. You try power factor and volt-var as your day-to-day voltage regulation mechanism, but you set this volt-watt active, but with a higher setting, like 105, 106%. So it will start reducing power only when voltage exceeds that limit. So kind of your backup mechanism. And we'll show it in this afternoon. In the IEEE standard, I think for volt-watt, the default setting is 1.06. It allows you to go up to 1.03, but default is 1.06. So the idea is that it will not be impact the operation in the day-to-day basis. It will only do when voltage goes really high. There is a question, does phase imbalance affect this? That's a very good question, and we are actually investigating to see how inverters responds to unbalanced condition. And so far, I think we tested 1 or 2 inverters, and looks like most of those inverters only respond to the positive sequence voltage. So they respond to the average voltage. So they don't inject VAR, almost average, same VAR in the 3 phases, responding to the positive sequence component only. Is VAR injection absorption depend on irradiance? The answer is no. As long as the inverter control board is operating, like it has some power to run its DSP board or microcontroller board, it can produce reactive power. However, most of the commercial inverters available in the market or installed in the field are designed to go into sleep mode during the sunset. So it wake up in the morning after certain DC voltage, generates the power for the whole day, and the afternoon, when the evening, when the voltage and power goes below a threshold, it goes into sleep mode to reduce losses during nighttime, also during losses for the transformers. That's how they are being designed. However, like right now, we are doing a pilot project with one of the utility that we intentionally, the utility wanted to see the inverter can provide reactive power support during nighttime. So nighttime, of course, there is no solar, no irradiance, but the manufacturer has to make some adjustment in the inverter operation. Like it has to be powered from the AC side. During nighttime, there is no DC power, so the control has to be powered from the AC side. Few other things has to be adjusted, and then it was able to operate in the nighttime and provide reactive power support up to it's a transmission connected system. So we have tested up to 30 MVAR during nighttime without any solar, of course. So yeah, theoretically it's possible if it's designed for that purpose, that you have to ask for it that I need reactive power support during nighttime. So it has to be designed or configured for that. There's a question, is it true that volt watt can control voltage more efficiently than volt var at times, depending on the X/R ratio of the line? Absolutely true. So reactive power will be effective if your X/R ratio is high, so you have more reactive impact of the reactive energy that you're injecting. And depending on the location, close to the substation, most probably volt var will not be that effective. On the other hand, volt watt might be. So yeah, absolutely right. Volt watt, depending on the X/R ratio, could be more effective, but at the same time, you have to remember that it will directly impact the kilowatt hour generation, which is the revenue. So unless you have some sort of agreement with the customer, having a very aggressive volt watt, you may get some pushback. Any other question or comment? So I'll not go through this slide. This is basically the summary of what I said before. These are the three main, most common or main important voltage regulation support functions. That's why I wanted to show it in one slide just for your reference. I would say that we take a break now. Still, we have a lot of materials to cover from session 3, and then of course we have this session 4, but hopefully session 4 is not that long anyway, so we'll be able to cover it this afternoon. So I propose that let's take a break for 54 minutes. Try to come back before the 2 o'clock so that I can start immediately at 2. The same thing we'll do, we'll stop the recording, immediately stop the recording.